Our next speaker will be Fiona Burnell from the University of Minnesota, who will be continuing your discussion on topology and strongly interacting systems.
Perfect. So I guess let me maybe preface this by saying that, we've had a lot of talks about, how to work on a specific material. And I'm more going to talk about tools that can be used to study a range of phases. So let me just remind you that, last time I sort of motivated that when we're working in the lowest Landau level, we should think about an effective field theory with this kind of action called a Chern-Simons action. And then we saw that this Chern-Simons action implies some interesting things about the state of matter that we're describing. In particular, it shows that we have particles, the sources of the gauge field, that have fractional statistics. So they're anyons, they're neither fermions nor bosons. And also that this system, if you put it in the right kind of boundary conditions, it will have a ground state degeneracy. That ground state degeneracy depends on the topology of the system. So I guess this pointer is also maybe out of batteries. So if anyone has another one. Okay, and so today I'm going to talk more about the things that we can do and understand with these types of effective field theories. And it's important to be clear, what is effective field theory for? So especially these kinds of topological effective field theories are really not helpful if your goal is to understand the energetics or like what's going on in a specific material. Because in my effective action, I didn't tell you anything about the structure of the orbits in the lowest Landau level. I didn't even tell you what the interaction was. I just sort of made this guess of what my particles are doing. So these kinds of effective field theories, for example, are not so good at answering the question, why is half filling in the lowest Landau level, right, different from half filling in the second Landau level? Okay, and we know it is, but that's a different kind of question. Thank you. All right. But what they are good for, and what they're very good for, is understanding what kinds of interaction topological states or topological orders could potentially be found in some material, and also describing the properties of these states, things like their Hall conductance, their statistics, and the ground state degeneracy. Okay, so I'm going to tell you about this kind of toolbox and maybe give some examples of how you can use it. So I'm first of all going to expand our toolbox a little bit to more general abelian states. And I'll tell you, some fun things that you can learn about, for example, the edge of your quantum Hall system in this way. And at the end, I'll say a few words about going beyond this word abelian and talk about non-abelian topological orders. Okay, so there's sort of a question, and this was, I think really motivated by the, very early on by the experiments in these fractional quantum Hall systems. I think that Rice needs a better supplier of batteries, actually. And the question is something like this. So, last time we talked a lot about this big fractional plateau at a third filling. But you'll notice that, there's a bunch of other quite prominent plateaus, right? At other fractions like 2/5, 3/7, 4/9. And there's kind of a pattern here, right? And so you might ask, how do I sort of understand what's going on here? And one of the pictures, which, is not a good description, I think, of these actual plateau transitions in semiconductors, which are very disordered. But one of the pictures that people like to think about is, well, what if, this theory here, has these quasi-particles that carry a third charge. And, what if as you're tuning the magnetic field, you're making more and more quasi-particles until suddenly they have to form themselves into some other kind of gap state? Okay. So how do we describe that state? So I'm not going to go through, at the same level of detail as I did for nu equals a third, how to think about this. But instead, let me show you the shorthand trick that we could have used to guess this action. All right. So step one. So this is so what I'm going to do is, this is the action that we motivated, with a parton construction last time, and it was a little bit involved. Okay. But now that we know that this is the right answer, how could we have gotten it, right? This is the answer of, I have a gauge field. It's coupled to some matter, right? It's coupled to some current. That current, consists of particles that are somehow filling Landau levels, right? And at the end of the day, this is what we got. So what's the hack to write down the right action for this? Well, let's start by just saying, and I apologize because actually this should be little a to be consistent with my notation down there. But let's start with, an action with just like a current that's like, oh, sorry, no, sorry. This is my electromagnetic gauge field, okay? And so we just start and we say, like, I have some currents, okay, that's coupled to the electromagnetic gauge field, right? And my first thing is I'm just going to re-parameterize the current. So, one thing that we know about a current in a gauge theory, so electromagnetism is a gauge theory, is that it is conserved, okay? This is like a kind of sacred law. And if it's conserved, okay, then what that means is its divergence is 0. And so I could equally well write the current as the curl of some vector, right? And that's just a convenient way of writing this conserved current, this divergence-free quantity. So we reparameterize the current, okay? That's just a trivial substitution of variables, if you will, right? And then we observe that, when this current consisted of particles that were going into some Landau levels, right? And we had our parton construction and so forth. The net effect of that is to basically take this little a, this vector field that we introduced to parameterize the currents, and give it a Chern-Simons term, okay? So again, this is kind of the cheap hack. There's many ways to talk about where these actions come from. They all agree on the final result, okay? But now, oh yeah, sorry, and here I've put in a number q in my model, q equals 1, and then this k, previously we thought of this as k, partons filling up k Landau levels, okay? And now, okay, so now this is an action, and this is just describing my 1/3 state. And if I wanted to add quasi-particles on top of that, I would now have to put in a new current that couples to this little a gauge field, okay? And so let's add this current here, right? So now I've actually dropped my electromagnetic field, and I've said, now these anions that are coupled to little a, well, there's going to be a bunch of them, and I'm going to need to describe their background state. And we just play this game all over again. We reparameterize this new current in terms of a second vector field. I call it B. This is great. It works. Current is divergenceless, okay? And then we say, well, let's add a Chern-Simons term, right? And, maybe I can pick a different level. I could call it M for my B's, right? And at this point, we're kind of agnostic about, what our B's are doing, and to think about a specific state, we need a specific choice for what our B's should be doing here. Okay, and now if I add back the charges, right? So I add back my original coupling to the electromagnetic gauge field, which was just through A, and I get an action that looks like this. Okay. Okay, so what's nice about this action? So if you pick m equals 2, this action, and I'll say a bit more about this in a minute, but so if you pick m equals 2, you can compute the Hall conductance and the particle content of this theory, and m equals 2, k equals 3, and you reproduce this 2/5 plateau, okay? And then you can play the game again to get other plateau in this sequence, and reproduce the phenomenology of the quantum Hall states that Janandra Jain explained using this composite fermion picture, for example. Okay. But now, so rather than tell you, in more detail about how you do this specifically for like the Jain sequence, I want to zoom out a little bit and talk about the general picture that this paints. Okay. Because this gives us sort of a general idea of the kinds of theories that we could get that might describe kinds of states that we could have in some Landau level, maybe not the lowest Landau level, right? Maybe even not a Landau level at all. but there's a very general picture here where I have some number of different kinds of Chern-Simons fields. I've called them AI. Maybe I can bring oh, no, I don't have maybe we can do this. Yeah, here we go. So these Chern-Simons fields, AI, okay? And I pick some number of I's, and the couplings, the Chern-Simons couplings, are conveniently encoded in a matrix. This is called the K matrix, right? And then I can also assign, different charges to these different couplings with the electromagnetic gauge field, okay? And this allows us to construct a whole bunch of different kinds of abelian topological orders, any one that you might want. But again, I want to emphasize, it doesn't tell us that all of these will be realized on some Hall plateau. Okay. But this is a very useful tool for asking kinds of questions about these kinds of topological states. And so, in particular, for example, you can use it to calculate bulk properties. You can calculate the charges of the quasi-particles that are coupled to each of these A's. You can calculate the Hall conductivity, and you can calculate the braiding statistics of these particles. And there's a hand-waving derivation of this if you like path integrals, okay? You can do this exercise. It's a quadratic action. You can integrate out the A's, for example, to calculate the effective electromagnetic response and get the Hall conductivity. And this is, this gives you these correct answers. You have to be very careful because if you do this in front of like your high energy colleagues, they will have a hissy fit because, it's sort of, you can't necessarily integrate out these fields. You're throwing away information. But in any case, this is a very quick way to write down a theory and calculate its properties. And so the thing that I want to tell you about for these kinds of theories is I want to talk a little bit about how we can use them to study physics at the edge. And this will tie in a little bit to stuff that I want to say at the end about non-abelian anions. Okay. All right. And so maybe let me motivate what I think is, an interesting general question here that you could ask, right? So Joel, told us that for quantum Hall, we have these extremely robust edge states. This is like they're so robust that they define our unit of resistance. And this is because, in the quantum Hall picture, you have this semi-classical picture. At the boundary of the quantum Hall system, the particles can only go one way, right? So they can't backscatter. This is extremely robust. And Joel also told us about quantum spin Hall states, right? Where you have these counter-propagating edge modes, and they're still protected, but backscattering is prevented only by a symmetry. Okay. So, you can ask, well, now I have this whole family of like purported maybe quantum Hall states that I could write down. And you can ask general questions such as, when do we get boundaries that simply cannot be gapped, right? Like in the integer quantum Hall case, can never be gapped. What does it mean for a boundary to be gappable, but only if a symmetry is broken, right? And for edges that can be gapped, is there more than one kind of gap that I could open up? And, I think when we ask this question, when do we have boundaries that are like topologically protected, can never be gapped out? I think a lot of people are like, aha, I know the answer to this. This is just a thermal Hall conductivity, right? Or in conformal field theory language, this is the central charge, right, which is related to an anomaly of the stress energy tensor in the, in the conformal field theory that we're talking about. And it is true that a non-vanishing thermal Hall conductivity means that you have an edge mode that cannot be completely gapped. But I think an interesting thing to note about this is that that is not the full story. And there's a really nice example in a paper by Mike Levin in 2013, right, where he pointed out that there are edge states that are protected where, I should say, what is the central charge? Okay, so the quick kind of counting argument for the central charge in these abelian theories is it's the number of modes that go to the right and minus the number of modes that go to the left, okay? And he pointed out that even when the central charge is 0, right, You can have situations where the edge cannot be gapped. This is not a statement about the edge cannot be gapped without breaking a symmetry. This is a statement about the edge cannot be gapped, period, ever. Okay. And so why is this? So to understand the full story, I need to tell you a little bit more about the relationship between how to open a gap at the edge and the statistics of bulk quasiparticles. Okay. So let me start with a single Chern-Simons field, okay, and remind you of why we have these, like in integer quantum Hall or Laughlin III, why we have these chiral edge modes at all. So here's our Chern-Simons action, okay, and I'm doing this on some region in space. And remember, our little field A, right? This was like this was a fiction, okay? A was a fiction, and the gauge invariance of our theory was a statement that we had created this redundancy in the Hilbert space, okay? Meaning that if you have a lack of gauge invariance in this theory, you're basically doing something very, very wrong at the level of this kind of freedom and defining, who's the physical electron and so forth. And so, what you observe is this Chern-Simons action. So here's the gauge transformation of the electromagnetic gauge field. And you plug this into this action, okay? And you see that the action is invariant under this transformation in the bulk. Why you can just, but this invariance involves a kind of integration by parts, okay? And so you get a contribution at the boundary. Okay. And so the way to think about this, this is a manifestation of what we call an anomaly. Okay. And the way to think about this is that is telling us that there must be something on the boundary, right, which also violates gauge invariance and like cancels this anomaly. Okay. And I should say, what does it mean physically that there's an anomaly? This means that our current, which was supposed to be conserved, supposed to be divergenceless, is not conserved. Okay, and so let me tell you a little story about this because it's one of my favorite digressions about one-dimensional physics. Okay, so you can ask, who can cancel the anomaly? And the answer, of course, is our chiral boson. And why is that? Well, the chiral boson famously is a theory that does not conserve current when an electric field is applied. Okay, so a chiral boson, how do we think about a chiral boson? I've drawn this little picture that says a chiral boson consists only of right-moving particles. So let's maybe put that back in a more familiar context, right? Here is a typical boson in one dimension, right? And so in this action, I would have the right movers and the left movers, coinciding at the origin. Right, but if you allow one of them to be shifted over in momentum space, you can think of this as right moving and left moving, branches of some Fermi surface. So we can take our fermions in one dimension, we can describe them as bosons, okay? And roughly speaking, you get this action, and you can think of right movers being on the right branch and left movers being on the left branch. Okay. So now let me just talk about this in terms of the bosonic action, okay? And actually, in this theory, right, you look at this action and you're like, hey, there's two conserved densities in this theory, okay? There's the total charge, which is the number of right movers plus the number of left movers. And there's the momentum, right, which depends on the difference between the number of right movers and the number of left movers, okay? And in our bosonic theory, that actually corresponds to two conserved currents. One is the electromagnetic current, and one is the electromagnetic current, right? You can see d mu j mu is 0. That's just equality of mixed partial derivatives. And then there's this other current, right? The left minus right current, which is called the axial current, right? And that's conserved due to the equations of motion. Okay. And by the way, this kind of argument, I think, was originally described by Eduardo Fradkin. So now we can put this in context, right? So what is wrong with this, with these two conservation laws, right? What's wrong with these two conservation laws? Well, the electromagnetic current is always conserved. But if I apply an electric field, right, and I shift my chemical potential, right, basically what that does is it has to take some of these left movers and push them over and turn them into right movers. So the number of left movers plus the number of right movers is always conserved, but the difference between left movers and right movers is not conserved, okay? And so this statement about this, electromagnetic current and axial current, which you can read about in terms of like loop diagrams in Peskin and Schroeder, from the point of view of condensed matter, you can really think of it as a very familiar statement, which is if you take like a 1D metal and put it in an electric field, the momentum is no longer conserved. Okay. But now we can see right away that if we cut off the left moving half of this picture, we really do have a problem, right? Because now, what happens in the bottom half of the picture here, where I apply my electric field, is that just the number of particles is no longer conserved, okay? And this is the reason that this chiral boson on the edge is, does not have a conserved current, okay? And happily, the lack of conservation of the current at the edge, and you can show this by writing down a theory for your chiral boson in which you couple it to a gauge field and looking at the effect of gauge transformations on that theory, and you can show that they exactly cancel the lack of gauge invariance in the Boltzmann-Simons action, okay? And so this current non-conservation at the edge is exactly canceled by the current non-conservation from the bulk. And so the moral of this story is anytime you see a Chern-Simons theory, right, you should think about it being accompanied automatically by these chiral bosons that live at the edge. Okay, so with that in mind, let me go back to this more general Chern-Simons action, okay? And here I have my K matrix, and I can ask what kind of boundary theory does this give me, okay? And this boundary theory has a piece which is just like dictated by the topological part, okay? And that is basically the dt dx part, right? Which tells us about the chiral bosons and how they talk to each other. And then it has a non-universal part that can be, velocity terms for these particles. Okay. And we want to ask, can I open a gap? I have some K matrix. I give you a K matrix, and I want to know how can I open a gap? How many different ways are there to open a gap in this system? Okay. And let me just. So I'm kind of like going over very quickly, but I think many of you will have seen some bosonization, right? And so how do we open up a gap in these kinds of 1D bosonic theories? Well, basically, the way that you do it is you add a potential involving a cosine of the field, okay? And what you want is for the coefficient of this potential to grow very large in the infrared, or maybe you just make it very large at the beginning, such that this cosine is going to take an expectation value, and now phi is going to be locked near the minimum of this cosine, right? And then you sort of want to think of this as like a harmonic oscillator, there's a gap. Good. But if you try and do this for your chiral boson, the cosine cannot take an expectation value. And the reason for this is very clear from the action. So if we look at this action, right, and the reason that these dx, dt terms are, contain this universal information is that these tell us about who is conjugate to whom, okay? And in this case, phi is conjugate to dx phi. And so that means that phi, at different locations in space, these phi fields do not commute with each other, right? And so you cannot consistently give cosine of phi a classical expectation value. Okay. What if I have two chiral bosons? So here's a theory with two chiral bosons. I've got a phi 1 and a phi 2. And importantly, I've put a little minus sign here. And when you put the minus sign here, I can actually write this action in terms of like a time derivative of the sum and a space derivative of the difference, okay? And in this case, right, the field that is conjugate to the sum, which I'll call theta, is the difference, which I'll call phi. So now we can see that actually, theta now commutes with itself as you would like. And so you can put a cosine of theta term, and it can have an expectation value, and you can open up a theta type gap. Okay. And if you, on the other hand, okay, we can also put a cosine of phi term, and this could grow large, right? And you can open up like a phi type gap, right? And you can think of these, if you think of the theta and phi fields, if you think of a typical lead energy liquid like charge and spin, you can think about these as, a superconducting gap and a time reversal breaking gap. Okay. So you can have one or the other, but phi and theta are conjugate, so you can't have both. Okay. So now you could ask, well, what if, so the chiral boson is totally non-gappable, right? These counter-propagating phi 1 and phi 2 is gappable. It is not topologically protected. But you can ask, well, what if I add back a symmetry? Okay. And so famously, if you add a Z2 symmetry to this theory, you can make it impossible to open a gap without breaking the symmetry. So for example, I could have a Z2 symmetry that shifts phi 1 by pi, but does nothing to phi 2, right? And under this symmetry, both of these gaps change sign. So that tells me it's not that I cannot gap the system, but if one of these guys gets an expectation, if either of these guys gets an expectation value, right, then the symmetry must be broken. Okay, perfect. So that brings me to the general story, which has a very elegant answer. So let me come back. This is my completely general Chern-Simons theory, and I have this K matrix which describes these universal terms or the commutation relations between my different phi fields at the boundary. And you can ask, like, what are the possible gap terms, cosine terms that I could write down? And the most general thing that you could write down would be that you just take all of the phi's and multiply them by some integer coefficients, okay, and take a cosine of that. And now it's not hard to, read off from the commutation relations dictated by this action, when can these cosine terms get an expectation value, right? And that is when this linear combination of phi's, commutes with itself, okay? And that is a condition that you can just compute using this K matrix, okay? And you can ask, well, when can I have, two different cosines, and they, when could they take an expectation value at the same time, okay? And that's this slightly different, condition on the, using the K matrix. Okay. And so now, I can write down all these cosine terms, and I can ask, can I fully gap out the edge, right? And the answer is, I can fully gap out the edge if I can write down enough cosine terms that all of the other linear combinations of these phi's with integer coefficients fail to commute with at least one of these things in the cosine terms. Now, the nice message about this, which actually goes far beyond abelian topological orders, is that you can view this as this gapability of the edge as a statement about the statistics of the anyons in your bulk theory, right? So let me remind you, I wrote this up really quickly. I didn't do the calculation, but from this K matrix, we can calculate the statistics of the bulk anyons, okay? The guys that source gauge field I and the guys that source gauge field J. And we can ask, what does this criterion mean in terms of these bulk anyons? And the meaning is that there's some particle, some combination of these phi fields, some quasi-particle, which is not a trivial particle, okay, but which is a boson, okay? So here I said pair, but there could be more than two of them in this combination, okay? And then the criterion that the second criterion basically means that if I'm going to have cosine terms associated with like the TA vector and the TB vector, and they simultaneously are going to have expectation values, that means that the mutual statistics between quasi-particle, the quasi-particle associated with A and the quasi-particle associated with B are trivial, okay? And so this statement about can the edge be fully gapped is in fact simply a statement about the statistics of the, about the set of statistics of the bulk theory. And what I need is to have a set of anyons that are bosons, okay, and which also have trivial braiding with each other, such that they braid non-trivially with all of the other anyons in the theory, okay? And there's a word for this. This is called a Lagrangian algebra, and it tells us exactly when our boundary can be gapped. Okay. Good. All right. And I should just say this picture is really, really general. Okay, so this statement about Lagrangian algebras is true not only for abelian topological orders, but general topological orders. And they can tell you about, you can use it to tell you about when a topological order has a gapped boundary to the vacuum, okay? And you can also use it to ask, maybe I have like the 1/3 state and the 2/5 state, on the left and the right, and I might want to know, is there a gap boundary between those? And you can use this same technology to answer this question. Okay, good. All right, so, oh yeah, I have paused for questions because I'm going to shift gears a little bit. Are there any questions at this point? Yeah.
So my question earlier, you were talking about the transcendent action and how it's used to predict things about the effects. And then you mentioned that it has some implication about the energetics. So why exactly can't we get like microscopic system?
Okay, yeah. So the question is, I made this comment that, the Chern-Simons theory tells us about, the topological order of the phase that we get, but it doesn't tell us about energetics. And let me clarify that, by energetics, I mean, you have a material and you want to know, is this material going to have a plateau when the Landau level is half filled, right? And the point is that that question depends. So, and I can tell you, well, at half filling, there is a consistent topological theory that could describe that state, okay? But, in general, right, so we know that at half filling, the theory is not gapped, it's gapless. And why, and sorry, half filling in the lowest Landau level, right? But the 5-half state, on the other hand, is gapped, and it's this topological state. And you can ask, why? What's the difference, okay? And the difference is not that, those guys would be, those systems would sort of be described in some way by like different topological theories, different kind of Chern-Simons theories. Rather, it's really a statement about how the Coulomb interactions projected into the second Landau level are different from the Coulomb interactions projected into the first Landau level. And I think it's useful to note that historically these Chern-Simons theories, the wave functions, there's pictures where you can build wave functions from conformal field theory, and all of these things were basically guesses, okay, about, well, here's something that would get the Hall conductivity right that we think will capture what's going on. And the way that these were checked was basically numerically, right? So now I want to know, is this, I can answer the question, can this happen, right, in principle? But if you want to answer the question, does this happen in my material at this filling, that you need to check numerically. Does that answer your question?
Yes.
Okay. Yeah. Oh, good. Yes. Okay. Yeah. Good. So this is like a picture which tells us, okay, how to construct these gap domain walls. So suppose that I want to understand whether there's suppose that I want to make a gapped boundary between two different topological orders, B1 and B2, okay? And a way to construct that gap boundary is if you take this picture and you fold it over, this is called the folding trick. Um, um, then if you fold it over, then you can see that that's the same question as can I build a gap boundary between a bilayer system with B1 on the top, B1 on the top and B2 bar on the bottom. Can I build a gap boundary between that and the vacuum? And so here what I need, and so here what I get to do is I get all of the anyons in B1, and all of the anyons in B2 bar, and I look for bosons there, and I see whether I can, condense enough bosons to kill everything, right? So the statement that my things that I'm condensing have to braid non-trivially with everything else. This is exactly the same statement. Like, when I Cooper pair electrons, right, I can find magnetic flux because, a flux that is not an integer number of half quanta, right, has some non-trivial braiding phase with this condensate of Cooper pairs, and that is an energetic disaster. And so I ask, do I have enough bosons to kill this off, right? And then in the unfolded picture, I might be condensing like, it's not that I'm condensing something, something over here to get to here necessarily. I might be sort of on this boundary condensing some stuff from this side, together with something on this side. So this is just a shorthand for, how you would construct these gap boundaries. I'm happy to talk more about it after. I think without a board, it's hard to say more than that. Yeah.
Previous slides over, you mentioned being able to fully gap a theory.
Yeah.
What's the difference between being able to fully gap and partially gap?
Yeah, good. So, so maybe let's take like a really simple example, right? Suppose that I went back to my story with just my two counterpropagating edges, right? And suppose that I added a phi3 here, right? And maybe phi3 is a right mover as well, okay? And so then the story would be that I can partially gap the edge, right? So I could add backscattering terms between phi1 and phi2, right? And if phi3 is also right moving, I can potentially add backscattering terms between phi2 and phi3, right? But basically, in that case, you wouldn't be able to kill off all of these gapless modes, right? So you might go from saying I have two right movers and a left mover to like I have a single right moving mode. So this kind of way of thinking, for example, can be useful in asking about things like edge reconstruction of like, different kinds of edges that are compatible with the same bulk theory. Yeah. Other questions? Yeah.
I have a question. We're supposed to take this interpretation that we can encode some sort of idea of all physics, these Turing time and time. But is there something preventing us from writing down a theory of like free anyons here? Free as in like some boring quadratic action that gives us mobile anyons.
So I guess I would say that so the first thing is remember an anion must be emergent, okay? Because we do not have, you go to a particle accelerator, yes, protons have charge a third, but they are not anyons, okay? They are still fermions. And so these anyons, once we have these fractional statistics, they have to be emergent. And that basically means, and the way that this Chern-Simons theory captures this emergence is, you cannot ever have a single, Laughlin quasi-particle, right? They're always created in, pairs, particle-antiparticle pairs, and they're connected by this string of the gauge field. And so I think from that perspective, okay, so, it's true that this is not a good way to think about, dynamics of these guys. And so if you want to talk, the other thing you can do is you can go to composite fermions, composite bosons, parton constructions, right, where you work with particles that are essentially fermions, right, and you're putting them into Landau levels or bosons, right? And you can think about constructing those states in that way, right? But of course, they're partons. And I think, if you want to say, well, what is the right quadratic theory, solvable theory just for anyons? I think you could say it is the Chern-Simons theory, basically. Because Chern-Simons theory has a constraint, charge, and flux, are the same thing. And so all of the, all of what can go on with those particles is really captured by this gauge field. Great. Let me move on. So I guess the second thing that I wanted to talk a little bit about, since I'm sure all of you have heard this word, and I want to make some connections to some of the things we've heard about in Moiré materials and why I think they're exciting. So I want to talk a little bit about non-abelian topological order, right? So yesterday we had this parton construction, right? And we had, I wrote down like this non-abelian Chern-Simons action. And then we said, well, in that case, K was 1, right, for like an SU3 gauge field. And more generally, we could say K is 1 for an SUN gauge field if I had more than 3 partons, okay? And basically, we said that that theory looks the same as a theory with abelian gauge fields where we pick K is N, okay? So this was this magical level rank duality that all of the non-abelianness kind of disappears when K is 1, okay? But then you can ask, well, what if K is not 1, right? What if K is bigger than 1? And the answer is, if K is bigger than 1, then you really do get theories that are very different from a Chern-Simons theory with abelian gauge fields. And basically what I want to tell you about is a little bit of the properties of non-abelian topological order and how to think about them. Okay, so if you read about quantization of non-abelian Chern-Simons theories, okay, the story looks really complicated and kind of intimidating. And so I want to start by telling you there's a really simple way to think about what's actually going on in terms of the result that we get. And so I want to start with, forget Chern-Simons theory. Let's just suppose that I have a theory with an SU2 symmetry, okay? And in a theory with an SU2 symmetry, we know how to talk about particles, right? We have to label the particles by their total spin, right? And if we have a particle with total spin that is not 0, right? And the total spin labels an irreducible representation of the group SU2 if you want the mathematical words. Now, if the total spin is bigger than 0, right? Spin a half, spin 1, spin 3 halves. We know all of these representations have multiple states, 2, 3, 4, etc. Okay? And we can't label a particle, we can't say, oh, in a system where I have an SU2 symmetry, and especially if I have a local SU2 symmetry, right? I can't label a particle in an invariant way by saying, oh, this is my spin up particle, right? Because I could do an SU2 rotation, I can turn my spin up into a spin down. But I can say it's a spin a half particle because I can't change the fact that it has spin a half, right? Unless I break this symmetry. And if the symmetry is a gauge symmetry, I can't do that. Okay. So this is the statement that we really need to label these guys by their total spin. And the second thing that you're familiar with from SU2 is, of course, if I take 2 particles that have different spins and I moosh them together in space, right? Because there are multiple internal states in these irreducible representations, unless one of the particles has spin 0, there's more than one type of particle that I can get out, where here type of particle is labeled by its total spin. Okay? And this obviously is different. This is the difference between SU2 and U1. In U1, if I take a particle with charge 1 and a particle with charge 2 and I moosh them together, I can only get a particle with charge 3, right? And so, you can talk about this as just rules for how the particles fuse with each other, right? And I would say, okay, I take 2 spin a half particles, and I could get a spin 0 particle or a spin 1 particle. And I take 2 spin 1 particles, I could get 0, 1, or 2, and so forth. Okay. Now, the important observation here is that actually, if you go back to what we know about, addition of angular momentum, you will see right away that the total spin that you get from mooshing together your 2 spin a half particles can be influenced by just doing a symmetry operation on one of the particles. Okay. So, for example, let's suppose that I start with a spin singlet state. Okay. But then I'm going to, come along and, something happens. I separate the particles and I apply SZ to the first particle, but not to the second. Okay. And then I bring them back together And now, just by applying SZ, so a symmetry operation, to one of my particles, I go from a state with spin 0 to a state with spin 1. Okay, so to make connection with these kind of anion models and these kind of space-time braiding pictures, let me draw this like this, right? So time is going up in this picture, and I start with 2 spin-1/2 particles in a singlet, and if all I care about is conservation of SU2, right, I could have pair created these from the vacuum, and that's the way to think of the bottom of this diagram. Okay, now I separate them, right? And I send particle 1 through some region of space where there's like a Hamiltonian that carries out an SC rotation. That's this blue box here. And then I bring them back together, right? And I try to reannihilate them to the vacuum, but I find that instead I have a non-trivial particle which carries spin 1. Okay, good. So now, to fully make the connection with braiding, I want to tell you about a nice perspective on how to think about what happens when we apply a symmetry. Okay, so last time I showed you this picture of the Aharonov-Bohm phase, right? And we noticed that in the Aharonov-Bohm effect, right, I have this solenoid, I have a flux, a magnetic flux, a flux of the electromagnetic gauge field, okay, or a flux of the U1 symmetry, okay? And we observed that, just by looking at the canonical coupling, this flux, okay, leads to a phase difference between the 2 paths in the electron that the electron could take, and this, phase difference depends on the total flux, okay? And if we look at this, actually, what is a phase? What is a phase rotation of the wave function? That is the action of our U1 symmetry, okay? So the moral of the story here is, I took my particle around the symmetry flux, right? And it got acted on with my symmetry in a way that depended on the total flux. And if you don't like that picture, there's a very, very concrete demonstration of the same effect that I can think about for lattice defects, right? So if I have, a dislocation in a crystal here, right? So this is a symmetry defect, in this case of translation symmetry, and I take a particle and I bring it around this defect. So it's going to go down by 2, right? It's going to go right by like 4. It's going to go up by 2, and it's going to go back to the left, right? And we can see that at the end of this process, because it went around this disclination, it was acted on by the translation symmetry, okay? So the mantra here is acting with a symmetry can be realized by basically braiding your particle with a symmetry flux, okay? And so now let's put this back into our picture, right? So now I've drawn, I've removed my blue box, and I've turned it into a blue line, which represents an appropriate symmetry flux of our SU2 gauge field. And now we see that, lo and behold, in this picture, where I created a pair of particles from the vacuum, I brought one around the other. In the abelian case, I reannihilated them and just got some total phase, okay? Now, I try to reannihilate them, and I find that I must have a non-trivial particle type, okay? And this is important because this means that these statistical braiding interactions in a non-abelian theory are qualitatively different than anything that you could get in the abelian case. Okay. And so this is something that people got really excited about, quite some time ago, because they were like, hey, look, this, braiding in these non-abelian theories is not just a phase, it can lead to a switch in the particle type. I should say that for SU2 Chern-Simons theories, okay, so maybe now we want to come back to quantum Hall, and we say we should be thinking about Chern-Simons theories, and we want to have this non-abelian Chern-Simons theory. Okay, so a lot of the things that we remember from thinking about the group SU2 no longer hold. Okay, first of all, the addition of angular momenta is very different. There's a maximum spin representation that you cannot get beyond. Second of all, there's no notion of a number of states, an integer number of states in these irreducible representations, okay? But the basic property that braiding can switch the particle type, that's still there, okay? All right. And so, why were people excited about this? Well, the idea is like these statistical interactions, that they're kind of interesting because this would potentially be a way to manipulate information in a quantum system that's, because the braiding is topological, it looks like it should be intrinsically robust to local noise. So maybe this is a good way to make a qubit, okay? But if you only have abelian states, this is a lie. And the reason is that there's all kinds of reasons in an experiment that you might get an overall phase factor in your wave function. And, in fact, in a very brief digression, I want to say, like, this was like a decades-long saga to do experiments to even detect the abrading phases in quantum Hall systems with abelian quasi-particles. Okay, so this is a picture. Okay, now my pointer situation is not so great. Okay, this is a picture that was taken from a paper by Mike Manfra's group in 2020. Okay, and the idea was, how are you going to like measure phases, relative phases of wave functions? Well, obviously you have to do an interference experiment. So this is a quantum Hall interferometer. And the idea is you're going to inject particles along the top edge, okay? And you're going to look at what comes out down here. And basically particles that come out down here can take one of two paths. They can tunnel through the left constriction, right? In which case they don't go around this Hall region in the middle, or they can tunnel through the right constriction and come back along the bottom edge, right? And obviously there's going to be a phase difference because your particle that goes along the edge, now has some statistical phase due to going around this inside region. Okay. Now, when you work this out, you see that the net phase of the particle that went around the box relative to the one that didn't depends the particle's charge. So it depends on the total magnetic flux in this box. So it depends on the area of the box. And obviously it depends on the particle's charge. And it depends on the number of quasi-particles that are inside this box as well. Okay. And in particular, isolating the phase that's just due to the quasi-particles to show this fractional statistics turned out to be very, very hard. So these ideas were proposed in the 1990s, basically, and it was only in 2020 that measurements that, I think were agreed to be fairly definitive were made by Mike Manfra's group, right? And what they see is, so you take this system, you can tune the area, basically by changing a voltage on a gate. You can tune the magnetic field independently, and there's a particular, just sort of due to the change in area, there's a particular kind of pattern that you expect to see here, and they see these phase slips, and the interpretation of these phase slips is that this is when a quasi-particle, and by the way, that's what these little swirly things are supposed to be in this picture, a quasi-particle hops in or out of the interferometer. Okay, good. So abelian phases, not so good, but non-abelian phases in principle should be more robust, right? Because this switching should be something that's not going to have other sources from your typical experiment. Okay, and actually now maybe I might be running out of time here, but okay, so this led to this idea, which I'm sure you're all familiar with, right, of like topological quantum computing with Majoranas. This is, very similar to thinking about Chern-Simons theory SU2 at level 2. And the point is that, I have two particles. If I thought of them having spin a half, right, they can combine to a spin 0 or 1. Okay, and we think of these as two Majorana fermions having a fermion parity. Okay. And then, in this case, just like in the SU2 group example that I showed you, it turns out that if I take, two pairs of these and I braid one around the other, okay, I switch the fermion parity of both of these guys. And so in principle, this could give you a kind of robust braiding signature that would be easy to see in experiments. In practice, there's a long saga. This also has been hard to see, I think mostly for materials-related reasons rather than the intrinsic reasons as for the abelian states. Okay, good. So maybe I'm going to go very briefly through this last part, but I just want to kind of point to and then ask me more if you're interested. I want to sort of point to, so this gave people motivation for wanting to realize non-abelian anyons, okay? And then there was a question, which is like, where should we look for non-abelian anyons? And this has been a really, really hard problem. So you might say, well, what about the fractional quantum Hall effect, right? And if you have really, really clean samples, you see this nice plateau at 5/2. And the idea is that this is, potentially a non-abelian state. Maybe you see a hint of a plateau at 12/5, which could also be another non-abelian state. But the sample quality here has to be extremely high. The experiments are very hard to do. And so I think, here there's been a lot of controversy about things like, measuring fractional statistics. So you might say, okay, if we really want to make these things, maybe we shouldn't just hope that we have a material that realizes them. So another interesting proposal is you can make them using defects. And there's a couple of ways to think about that. So for example, it turns out that if you have an abelian quantum Hall state in a band of Chern number 2, okay, lattice defects can actually have some of these non-abelian properties. So they're not anyons, they're extrinsic defects, okay? But in terms of the way that they combine and certain actions under braiding, they have similar properties, okay? And this is, so this is a paper from Barkeshli and Shi. You can think of the chiral p-wave superconductor and a vortex there, which is a kind of extrinsic defect, okay, as another manifestation of the same thing. Another variant of this is you might be able to make something like non-abelian defects in one-dimensional systems. So this is, famously, Microsoft has been working a lot on these superconducting wires, okay, where you, again, make something like a bound state that has some of the properties of a non-abelian anion, and you can make networks of these things to braid, okay. Another variant of this idea, maybe you want something more than a Majorana, okay, is that, maybe, so this comes back to our more than one kind of gap idea, right? So we know that in some of these systems, right, if I have like a phi1 going to the right and a phi2 going to the left, right, I showed you that in that example, I can have two different kinds of gaps, right? One of them corresponding to like a superconducting gap, okay, and one of them corresponding to a time reversal breaking gap. And we also said that these two gaps are associated with locking fields that don't commute, so you cannot have them at the same time, okay? And that turns out to mean that if I make an interface between these two kinds of gaps, there is a bound state here, which again, looks like a defect, a kind of a partial version of a non-abelian anion. And this proposal was made a long time ago. And the reason that it was really hard to do is if you are working with like gallium arsenide in a 30 Tesla magnetic field, in practice, you're going to have a very hard time inducing a superconducting gap, right? So you want to take your material and you want to induce superconductivity in part of it. But if you have a background field of 30 Tesla, that's really hard. And this is one of the reasons that from the point of view of device physics, these quantum anomalous Hall states, okay, which can exist at very low fields, are extremely exciting because I think they open up a possibility of revisiting some of these roots. And the third thing that people have been able to do lately is, maybe you don't want a material, maybe you're not that fussed about a material. Maybe you just want non-abelian anions. You just really want to be able to do these complex braiding operations. And then, in fact, for some kinds of topological orders, you can basically prepare these states on a quantum computer. So there's been a series of experiments from a collaboration between the Harvard group and Quantinuum, where they have prepared sequences of the, prepared states of these types, okay, on the quantum processor. They can actually prepare ground states and also excited states, and they can demonstrate characteristic kinds of braiding that are specific to the non-abelian context. Okay, great. So let me end there. Basically the moral that I want you to take away from this talk is that these effective topological theories, these effective Chern-Simons theories, even though it's hard to directly connect them to a real material in a concrete way, they can be very useful because they describe the universal properties of our system. They describe the particle types, the statistics, and they can help us understand the kinds of edges and the kinds of gaps in these edges. Okay. And that, when you think about the whole range of the kinds of topological orders that could happen, right, and you could try to engineer, some of these are non-abelian, and this is really qualitatively a different thing from abelian topological order. Okay, and that's where I think new kinds of materials, and especially new kinds of materials that have, fractional Hall physics, can be really exciting. All right, let me stop there.
Are there any questions?
Thank you. That was awesome. I have a question about seeing anomalies in physical observables. I'm thinking specifically of something like the framing anomaly, which I understand is kind of important for anyons because it comes from the chiral central charge. But I was curious if that shows up in things like the like thermal Hall conductivity or Hall viscosity or something like that.
Right. Okay. So yeah. So things like the Hall conductivity, Hall viscosity are they're responsive to things that you can sort of view them as like anomalies in the conformal field theory. So central charge is anomaly of the stress energy tensor. The framing anomaly, which is definitely something that we think about for Chern-Simons theory, it's a different kind of obstruction, actually. So it's an obstruction so the framing anomaly is basically this idea that if you have a particle, I drew these particles and I drew them at the end of Wilson lines, okay? And I drew these lines as like really one-dimensional lines. But if you have a particle that has, statistics with respect to itself, when I take this line and twist it, okay, that introduces a phase. And so actually to do this right, and this was something that was famously pointed out by Witten, to do this right, I really am not allowed to draw a line, I have to draw a ribbon, okay, to keep track. And that means if you kind of delve into the details of the action, this action is not actually topologically invariant because you need this ribbon. Okay, so what does that mean? So one way to think about what that means is that some topological orders, so I think many of you have seen things like the toric code, right, or generalized, Kitaev models with quantum groups and so forth. Some of these topological orders, like and this is, the ones that they can do on these quantum processors easily, can be written on a lattice with like nice commuting projector models, okay? And they can admit, fully gapped boundaries. And some of them cannot, right? And so, the framing anomaly, if you like, is an obstruction to writing something as a commuting projector model, basically because you need the ribbon and, the commuting projector only gives you lines. And I think that is also, in fact, associated with an obstruction to having a gappable boundary.
It means you need a regularization, right? Essentially.
It's an obstruction to having this lattice regularization. But I mean, so it's not that you can't write a lattice model, of like a chiral Chern-Simons theory, but you can't do it in this way where you can get to something that, is kind of like, it's kind of like a boring ferromagnetic limit where you're just like, here's the ground state. It has eigenvalue 1 under all of these things, okay? And it turns out that criterion is actually the same criterion as saying that, the system admits a gapped edge. So they are in fact correlated. Yeah.
Thank you. That was...
Thanks for the nice talk. So I was just curious, as you described from the point of view of the K matrix using the chiral positions on the edge regarding their constant on the gapability, as well as I guess it also describes their like hindrance to condensation. So can the K matrix formalism can also describe possibility of condensation inside the ball, for example, between the half integer versus the 1/3 integer filling. In one case, we can have pairing, another case doesn't.
Oh, yeah. Okay. So you're talking about like,
Inside the bulk, like in one case, we can have like pairing theory in the bulk, like
right. So you're talking about like composite fermions and pairing.
Yeah.
Yeah. Okay. So there's certain kinds of condensation that this can describe really well, right? So here's the kind of condensation that this can describe really well. Okay. Imagine that I have the toric code, which is, and then I want to trivialize it by adding like, a parallel, a field, a field, just a magnetic field X or Z along the edges. Okay. So that you can describe, very nicely in terms of a condensation transition. You can write, kind of in these field theoretic language. If you want to talk about the Fermi surface associated with the half-filled Landau level, right, then you can't, you need more than the Chern-Simons action, right? Because you can't throw away these gapless, fermionic modes.
Okay, it's not then just the Chern-Simons action.
Yeah, that's right. So yeah, when you go, half filled, you then need to add back in these matter fields because they're gapless. Yeah.
And another thing in terms of for example, the double Chern-Simons theory, for example, for quantum spin Hall system.
Mm-hmm.
So is the K-matrix formalism can be extended there, and how that can describe that the edges can be gapped?
Yeah, perfect. Actually, yeah. So good. So the K-matrix for quantum spin Hall, I probably should have said this like more clearly. Okay. Yeah. So you could think of this as a spin Hall system, right? So you could think of phi1 as my electrons with spin up, right? And they see a Landau level with the field going this way. And you could think of the phi2 as electrons with spin down, and they see a magnetic field going this way. And and this minus sign is super important, right? So if I put a plus here, I couldn't have done this. Okay. And so this minus sign is telling us that the directions of the fields are opposite, right? And then one of these gapping terms, right? You would think of as backscattering, between the two spins, and the other one is again this Cooper pairing backscattering.
Okay.
Yeah, and so that's right. So in this case, there's kind of another thing about this is you sort of see that this K matrix looks like two. In that case, I would pick K equals 2. It's like 2, 0, 0 minus 2. Well, okay, sorry. I would say K 0, 0 minus K, depending if I'm doing fermions or bosons, right? And if I write it in the theta phi basis, it looks off diagonal.
Okay.
You have to be a little bit careful making those transformations.
Okay, thank you.
Yeah.
Let's thank Dr. Burnell again.